presentation. My name is Will. I'd like to introduce Christopher Neugebauer. He's going to be speaking to us today about guardrails, an alternative view of working safely in Python. Please welcome him with a warm round of applause.
Hi. My name's Chris. I'm on the board of the Python Software Foundation. I'm not talking on behalf of them today, definitely not. I also run a small conference in Northern California called North Bay Python. Get along to it. It's in April next year. Can't see my screen. Okay, so before I begin, I want to mention that some early slides are going to include some historical photos of non-severe accidents in motor races. If you want to look away for a bit, it'll be pretty obvious when you can pay attention again. I'll be talking about programming at that point. So this is a talk about how we choose to structure our programs and about how we communicate the structure of programs and libraries to others. It's called Guardrails. And I also want to warn, this talk is very conceptual. You're going to need to think about how to put what I'm talking about into practice. I'm really sorry about that, I really am. So let's talk about Grand Prix racing. In 1928, the National Automobile Club of Monaco, that's this tiny country marked out by the yellow line here, became involved in a regulatory dispute. Despite running the very successful Monte Carlo rally in the nearby hills in France, the club's efforts to be recognized as a national body by the International Motor Racing Organization at the time was disputed by the French on the basis that Monaco did not itself host any motor racing events and instead ran all of its events in France. The Monaco Club immediately sought to rectify this, not letting the country's area of less than 1 square mile getting in the way. They picked the 2 widest roads in the city as the basis for a racetrack and started holding the Monaco Grand Prix. The problem is that those 2 streets were directly next to the harbor. The first event in 1929 was successful, and so they had to run it again and keep rerunning it. This photo is from the 1931 event, and you can see the logistical challenges here. There's trees on the left of the street, there's the harbor on the right. This is really not a very sensible location for cars to be driving 100 miles an hour. But they needed to run this race here so that they could have control over the rally, which was the race they actually cared about. And you can see up the back here, you can see that there's like a hill there. It's got a corner, and it's got a significant number of direction changes that lead onto this harborside straight. And there's a braking zone and a turn that would leave you pointed at the harbor until you recovered and pointed back towards the racetrack. Now, you see on the right here, the only thing that kept you out of the water was some sandbags and ship moorings. An incident was only a matter of time. In 1955, Alberto Ascari misjudged his travel down the hill and only managed the first of the 2 direction changes and flew into the harbor. Thankfully, he was thrown from his car, seatbelts not being a thing at the time, and safely swam to shore. Australian driver Paul Hawkins managed the same thing in 1965, somehow going over the top of the edge of the circuit, which is now marked off with hay bales instead of sandbags. Much safer. But clearly something needed to change. Hay bales were not enough, and solutions like portable concrete barriers, which were good for stopping cars from going over the edge, had undesirable side effects. The solution came in the form of the steel traffic guardrail, which was marketed at the time by the Armco Steel Company of Southern Ohio. The W-shaped cross-section absorbs head-on impacts slowly, and by bolting spans together, impacts can be absorbed over a significant distance, which would reduce the travel of the barrier at the point of impact itself, making it far more likely that the car and the driver would remain within the bounds of the circuit. And this was remarkably successful. By 1971, much of the circuit was surrounded by Armco barriers. While that section at the bottom of the hill remains a hotspot of incidents, there hasn't been an incursion into the water since 1966. But beyond safety, the presence of Armco barriers had some significant side benefits. By being as tall as the cars, they gave visual indicators of where the track limits were, allowing drivers to brake more precisely. Racers and cars adapted, and within the decade, speeds at Monaco exceeded the pre-Armco days. Barriers also greatly reduced the scope of incidents at the racetrack. Cars would now remain within the confines of the track. And this predictability means that today, marshals are able to clean up after most accidents in a handful of minutes. And so thanks to their deployment in racetracks, today Armco barriers are used throughout the world as a way to reliably stop people from driving off the road in otherwise dangerous places. Now that's enough about talking about drivers and their difficulties with the C. Let's talk about programming and our difficulties with the C. More than any other programming language, C shapes the way that we think about writing software, and that's not without its consequences. C was deliberately a very small language, and most features in the language roughly correspond to the features of one specific CPU. The remaining features were built around code organization so that you could keep your programs in your head. This stood in stark contrast to other languages at the time that were not focused on the computer's capabilities, but rather the domain they worked in. Think COBOL being there for business applications or Fortran for scientific applications. Now, access to the full capability of your computer was a great thing, but being able to do anything that your CPU can do means that you're able to do anything that your CPU can do, including the things that are undesirable. It's easy to make something that doesn't work entirely as intended. So this is some reasonable looking code, but it can easily access memory that it's not allowed to, and when it does that, your program will die. You actually have to think about what your program is doing in order to avoid an error that stops execution. And all too often, this means that the intent of your code is obscured by defensive error handling. Or to put it another way, the act of understanding the effects of a program or how to use a language or library effectively is not the same as writing the code itself. It's not trivial to use a function in a C library without reading the documentation for that specific function. This might sound flippant, like we should definitely read documentation, but documentation therefore has to convey all sorts of minutiae that get in the way of thinking about what your program does. The consequences of not deeply understanding the contract of a function in C are worn by you, and they can frequently be unpredictable. And the first generation or two of languages after C sought to solve incremental problems: better code organization, better portability, better text processing, no need to compile, better data structures. And each of these languages, certainly in their early days, were geared towards the same philosophy of programming. Your code has a universe of effects, and it's up to you to make sure that your program doesn't touch the dangerous or broken ones. So take this two-lined piece of code of Python, for instance. I count at least two potential error scenarios in this code. What if example.com times out or is unreachable when you request it? And what if that URL doesn't return a valid JSON object? Now this code runs just fine on the happy path, but it's up to you to infer where the errors might occur and program defensively. So you can handle it with a blunt instrument, but this is really no better than the first case, other than you getting to write your own error message. Like, who cares? Just throw the exception. Or you can start scoping your exception blocks less tightly, and that tends to get tedious. In Python, your options are to either be permissive and let your routine die weirdly, or to be exceptionally defensive and handle every single error scenario. If you care about your programs not throwing exceptions, you should be doing the latter, but the tools that we've grown to use require us to predict where exceptions are going to occur and fortify the code where we think exceptions are going to occur. And that's what it means to work safely in Python: producing code that doesn't blow up, end unexpectedly, or have unpredictable behavior. And it's where we as programmers have to do the work to ensure that our programs behave correctly, and then we have to do the work to communicate how to use our programs correctly to our users. Or put another way, we have to document what our program does and how to make it do what it should do, and we need to test things to make sure that they do the right thing. And neither of these things are bad in and of themselves, but without appropriate tools, they're incomplete and insufficient. So the general approach to testing is that you write a bunch of cases, and each case represents a fraction of the code paths that your program could take. And we definitely have tools that can tell us about how much of our code base was exercised under test conditions. That's what code coverage is. But this approach to testing is invariably reactive, even if you follow test-driven development. If you notice an error condition after the fact or some code that you didn't cover, you still need to patch it with other tests because you haven't considered the full scope of bad behavior. And code coverage is only a useful metric across your own code base. It doesn't tell you anything useful about how your dependencies will interact with your code when you use them. Making a test suite that covers 100% of your dependencies code paths that your code paths can exercise, it's basically a futile exercise. Do you know every library you use will throw an exception? It's just not something that Python is very good at communicating, and it makes guaranteeing that our code is safe a process of guessing. And because most Python code does not communicate its structure completely, this means that instead of documentation that can focus on use cases and intent, you must explain the shape of your library or program before you can explain how it works. But this documentation is decoupled because the act of explaining how to program is separate from the act of programming itself. If a program evolves, but the documentation doesn't, then users can't figure out the structure of that program, let alone how to interact with it properly. And most failure cases are these structural failures, rather than misdocumentation within a correct structure. So this is ineffective. The normal way of writing code is communicated implicitly, and the only foolproof way of determining that structure is by interacting with it. Because when structure is not revealed directly, discovery is inherently a process of trial and error. Communicating structure and interacting with that structure should not be separate acts. What we need are tools that communicate structure for us, make it clear where the safe places to work are, and leave errors predictable. What we need are guardrails. So what do guardrails for computer programs look like? Guardrails for programmers are the same as guardrails for cars. They use structure to show you what's guaranteed to be safe. They limit the range of undesirable consequences, and in doing so, they make it easier to reason about possibilities. In short, guardrails are features that use structure to show you what is possible and what isn't, and in doing so, they guide you towards more correct programs, often by letting our computers figure out automatically whether we're entering unsafe territory and ruling those spots out. Now, over the last couple of decades, rather than adding features to let you take advantage of new things that Python couldn't let you do at all before, Python has steadily introduced guardrails as first-class features in the language. These are tools that help us interact with Python better and communicate our intent better to others and to avoid undesirable side effects. So let's look at 3 features of Python that you may already be familiar with and explain how these features serve as guardrails. So the first one I want to explore is the with statement. And to explore that, we need to look at the risky behavior that it previously replaced. So with statements are used to handle resources that need to be acquired or released. These are things like locks or file handles or sockets. It's actually really hard to get the life cycle of these objects correct. Say you open a file, you write to that handle, and then you close the handle. If that goes well, everything is fine. But what if it doesn't go okay and you can't write to the file and you get an I/O error that blows everything up? Well, that's where things start to get difficult. Where do you handle that I/O error? Do you put it outside the try except block? Well, that's really good unless you want to propagate that I/O error. So you might put another handle.closed inside the except block, which is slightly more correct, but you can see it's starting to demand a lot of the developer to get this exactly right. And so Python added a thing called try except finally. Whatever's in that finally clause will get run when you leave the block. And this is great for making sure that resources are all cleaned up properly when you're done with them. But there's some problems with it. Firstly, you need to know that try finally exists, and most people don't. It's difficult to read. Like, what happens? Does except get handled before or after the finally? It's not obvious from reading the code. And the other thing is that you can code with just try except and forget to use finally. Or you could forget to handle the possible exceptions at all and have something that looks complete at first glance but actually has subtle bugs that are not revealed. Basically, it's a trivial feature, but incorrect usage is more accessible than correct usage, and so is likely a source of bugs. So we got the with statement instead. The handle for a resource is valid when you enter the with block, and it becomes invalid as you leave the block. You get a visual reference to where it's safe to work with a handle and where it isn't. The with statement is a guardrail. It uses structure to show you the life cycle of a resource. It builds correct error handling into the structure of the code so that even if you don't do any error handling yourself, the resource is still managed correctly for you. And it makes it even easier to reason about where to put your exception handling. If you need to have access to the file handle itself in your exception handling, then you put the try except block inside the with block. And if you don't, you do it the other way around. And you can infer that and how it gets used from how it is structured visually. It actually becomes much easier to reason about this execution order. Because Python is showing you how to use its feature, it's actually easier to write code that gets it right the first time than it is into stumbling into correct behavior through trial and error. And it's also a guardrail that you can build into your own code quite easily. Look up the docs for contextlib.contextManager if you want to see how to do that. Secondly, async functions, which I think are interesting because they're an example of a way to introduce guardrails for a piece of machinery that already exists completely within the language. So async functions can only get called within an async context, either by an event loop or by another async function. The async await syntax gives you tools to make sure that you aren't using async and await, also that you are using async and await in the correct way. You can only await a call if you're in an async function. This both makes it clear that you need to use async functions together as a collection of things, but also it gives you some structural indication of where you're yielding control back to the event loop. And this compares really favorably to the previous way that async coroutines worked in Python, which was to make use of the existing generator machinery within Python and this yield from construct. It's not immediately obvious to somebody who doesn't have access to your source code that this function here is an async coroutine, but it is. To effectively describe something as asynchronous, previously you had to either provide docs that pointed out that something was a coroutine, or you could use names and say that it was async, or both. And there's no language level barriers that prevent you from accidentally awaiting something that isn't itself awaitable in the same way. Async await gives you both a convenient programming construct that lets you communicate that you're doing things asynchronously, but it's also one that lets Python verify that what you're doing actually makes sense. Now, guardrails don't just show you spaces that are explicitly safe, they also make it clear where things are not safe. Decorators show you that a piece of syntax that's normally straightforward to understand is about to be subverted, and that you need to make extra effort to understand what's going on. They highlight places of risk rather than lack of risk. Now, decorators exist because Python lacked features like class methods or static methods that other languages have built in. But it was possible to implement these things at runtime. But to do that, you would need to define a method, and then after defining the method, assign the decorated method back to its original name. And there's a lot to hate about this particular pattern. You're changing the semantics of a feature of the language at runtime, but the feature is definitely useful and it should be available. Now, what's particularly bad here is that the confusing thing happens out of sight of where you're defining something that looks like it should be doing something normal. And if your method is really, really, really long, it can be difficult to somebody reading the code to notice that this decoration is even occurring. Having the decorate syntax available in Python means that you can put the thing that's potentially confusing up front, and it makes it more obvious to people who are reading your code what is going on. But in and of themselves, decorators still don't tell you what's being changed, just that something is going to be changed. If you're writing your own decorators, it's still not immediately obvious whether your decorator is going to return a similar function, like class method would, or if you're going to modify things further, like property would. And this is where another one of Python's guardrails can come in. You can use static type hints to communicate structure in a way that will be communicated to people who read your code. If you have a decorated thing that's going to behave broadly similarly to the function that you've written, you can use bounded type vars like this to show that. And then it can be really clear if you're doing something that's completely unexpected. So Python has been evolving as a language. It's gone from following in C's footsteps, being an open field where all possibilities are open to you, and it's up to you to figure out whether something is right or wrong just by playing around with it, to becoming a language with constructs that show you how to safely use them, and to highlight risks or unexpected behaviors where they occur. But there's still a lot of historical baggage in the language, and you have to coexist with this historical baggage. But you can build your own guardrails into the interfaces you develop, and you can experiment with other people's interfaces using defensive coding techniques based on those guardrails as well. So doubtless you've seen an example like this. It's a thing that's used to trick beginners, right? Like, what happens when you make a list, you assign that list to another variable, and then you amend the second list? It's a trick question because there is no second list, and Python treats variables as references to objects, so a list and another list point to the same object. And this is true for built-in data structures like lists, as it is for instances of your own classes. And because you're all experienced Python developers, you know to avoid this in your own code, right? But what happens when you import somebody else's function and you pass your mutable data structure into that? At that point, you are trusting that the implementer does what they say they're going to do and that nothing unexpected is going to happen. And much of the time that works out, particularly if you have good tests against that library. But what if you want to have more guarantees? Consider using immutable data structures. Python has a lot of them built in. If you've got a list, pass in a tuple instead. If you've got a set, pass in a frozen set. If you've got a dictionary, consider rewriting your code so you've got immutable data structures. Key value pairs in a set can be rewritten as a concrete class using frozen data classes. These are really easy to use and should replace like dictionary-based configuration wherever you're using it. All of these structures enforce immutability at runtime. So by passing in these sorts of structures, you'll discover through errors being raised everywhere that changes are being made and you need to work defensively on your side. Through experimentation, at the very least, you can discover if you need to copy things or if you need to plan for contingencies. But what of your own interfaces? Static typing is quite a powerful guardrail. You can directly express to your consumers exactly what operations you're going to perform on an object and let them make their own decisions. If you're dealing with standard data structures in Python, there are abstract types in the typing module that cover immutable and mutable versions of these without depending on a specific structure type. So you can swap in a tuple or a list for an immutable sequence, or a sequence in this case. But what if you've got a class of your own? Well, recent versions of Python support structural subtyping, much like Go has, through a thing called protocols. So if you have a class that has an interface like this, you can write a protocol interface that describes the things that your function is going to work with, and then your type checker can verify that your class matches the protocol. And more importantly, it can do that for classes that you didn't write yourself and that somebody else wrote in contexts where they weren't aware of your type hierarchy. And this is great, but this one doesn't help with immutability, but you can fix that as well. You can just use @properties in your protocol, and that makes the type checker verify that you aren't writing to that attribute. With protocols, you can make your contract with your code's consumers more explicit. You can show them exactly what parts of the interface you're going to use and what you're going to do with them. And you can automatically verify that your side of the contract is correct, and your consumers can get a clearer idea of what it is that they need to test. And the last idea I want to touch on is the big one. I've been talking about exceptions a lot. Expressing and handling error states. Like this is what working safely is about. Making code that doesn't fail randomly because you failed to predict that a certain library would throw an exception. Which is difficult because Python's most obvious tool for handling errors is the exception. And it's really not a very good one. Exceptions interrupt the flow of code. Handling them efficiently is not particularly easy. And for the purposes of this talk, it's also unpredictable when they can occur. Like, exceptions are meant for exceptional situations that need special handling. That's why they're called exceptions. But Python uses them for most errors. And this unpredictability is not a new thing in programming. Like, Java has had its own guardrail for handling exceptions since the early days, this thing called checked exceptions. You can declare that a method throws in a certain type of exception, and then somewhere in the call chain, you have to catch that exception, otherwise your compile will fail. And this sounds great until you have to catch 6 or 7 different sorts of exceptions, and your code tends to end up being more exception handling than actual logic. And if you're dealing with a situation where error states are actually part of the normal and predictable flow of your code, you have 2 choices. You either have to code defensively, checking to see if something's valid before you do the thing, or you have to litter your code with exception handling. And this actually makes us complacent as to when errors are likely to occur. It's much, much easier to write Python code that just ignores the need to do this. And like, I've lost track of the number of times I've let code that effectively lets an obvious exception into prod because it was easier than remembering what functions would raise a value error. A trick that's popular in functional languages and more recently in Rust is to use result types from functions that might have errors. The basic idea is that a function can either return a success or a failure value, and your code has to acknowledge that before it can read the value. In Python, you can do this with union types from the typing module. If you want to code quickly and you can tolerate your program dying, you can do that explicitly with an assert. You're saying that an exception might possibly get raised by this specific line of code with a construct that people are familiar with. Or you can use conditionals to handle it like a variable. And that's it. The type annotation here shows you that there's an error condition to handle, and you know that you have to handle that error. And more importantly, the type checker also knows that there's an exception or an error handle that needs to happen, and your code won't pass type checking until you write code that acknowledges that possibility. This gives you so many more guarantees than you'd get if you solely used exceptions, and it also lets you reserve exceptions for cases where it doesn't truly make sense to continue on. So both immutability and result types do a couple of things that let you work safely with each other's code. The first is that by conveying structure in code that you can read and a computer can verify, it means there's less need for documentation that explains edge cases. If a function won't mutate an argument, you no longer need to explain that. If a function can return an error as a return value, then that can automatically be verified, and you don't need to explain that an exception could possibly occur. And being able to verify that you're handling all possible output cases from a library means that you can actually trust that code coverage is giving you a useful metric when you interact with that library. And that's a selection of 5 examples of guardrails. These are all examples of using programming constructs, context managers, async, decorators, and types to convey the structure of functions to the people who call them so that you can understand what you need to test and you can focus on documentation to give tactical understanding rather than merely understanding the structure. And these examples show that Python cares about using structure to communicate how code works. New language features are more often than not features that give humans better ways to understand the structure of their code, rather than simply expanding to allow all the features that our computer might have. And sometimes these are duplicated features. The first way to do something might be a way to enable behavior at all. Think generators for async. Think try finally. But these are really features that are there should you happen upon them. Context managers and async await actually show you how to use them, so it's clear from reading code that you're using things correctly. And that's how you should be thinking about selecting which Python features you use into the future. Python gives us guardrails and gives us tools to make our own, so we can spend less time understanding the space we can work in and actually doing that work. And just as Python gives us the tools to work more safely, we ourselves can structure code so that people who interact with our code can understand what assumptions we've baked into our code just by looking at the structure we expose, allowing them to write safer code with more focused tests. So yes, testing is still important, but having verifiable structure tell you what is possible and what isn't means that you don't have to write as many tests. And if there's no chance of an exception popping up, then you don't need to test for exceptions probably popping up. Documentation can, rather than describing the structure of a function, focus on the why and the how. Documentation still needs to exist, but the focus no longer needs to be on things that a computer can understand directly for you. Your documentation can become tactical or communicate intent instead. So signs are, in most cases, we've outgrown languages or frameworks that merely expose the capabilities of our computers and then trust us to understand the structure that we need to put in place to harness those capabilities. Instead, languages that give us constructs that let us use computers safely are starting to take hold. Python, being a language that emerged in the shadow of C, but has stayed relevant for more than 30 years through this change, gives you both options. So you can do whatever you want and wear the risk of unpredictable errors, or you can use the guardrails. And that's my talk.